Hello, welcome to my channel. Welcome to Rehandran. So, in this video, I'm gonna solve exercise problem from chapter 3, practice exercise 3.3 from elements of electromagnetics, and this is on the topic vector calculus. So, in this practice exercise problem, the problem is to determine the gradient of scalar fields. These are the scalar fields given ABC. U equals to x square y plus xyz, v equals to rho z sine phi plus z square cos square phi plus rho square, and C is a scalar field f, which is equal to cos theta sine phi ln r plus r square phi. Okay. So let us first define what scalar fields, what's a scalar field, and what is a gradient. So in electromagnetics, there are two kind of fields we have to know to understand the orientation of electromagnetic fields and to get the corresponding values um, in a defined coordinate systems. We have to understand what a scalar and what a vector is in terms of fields. So because electromagnetic field, the subject of our interest is electromagnetic fields, so we have to understand what a scalar field is, what a vector field is. And in advanced electromagnetic fields, there is a term called tensor analysis, tensor fields. So in future, uh, if I am able to understand tensors, I will discuss it in my videos, so stay tuned for that. So now, scalar field, what is a scalar field? So a scalar field is a mathematical function that assigns a value to every point in space, but not in certain direction. It doesn't give any sense of direction. It just um, appoints value in every direction, in every point in space. So scalar fields have only magnitude. So scalar fields only have magnitudes, no direction. So if we wanna say define a scalar field in mathematical terms, how are we gonna express it? So the mathematical expression can be written as, so this can be interpreted as a scalar field where x y z are spatial coordinates. So x xyz are spatial coordinates. And now there are many kinds of scalar fields. So scalar field can be discrete or continuous, and our main focus will be on continuous scalar fields. So continuous scalar fields. Continuous scalar fields, there are many examples of continuous scalar fields, like temperature distribution, temperature distribution, potential distribution. um, Continuous pressure in fluid dynamics, the continuous distribution of pressure in fluid dynamics. So pressure distribution. So these are the well-known um, examples of continuous scalar fields. Scalar fields have only magnitudes, no direction. So scalar fields can also be defined like this, that distribution of scalar quantity with a definite position in space-time. There are also other examples of continuous scalar fields like refractive index, refractive index of stratified medium, light intensity, light intensity in a room, pressure, atmospheric pressure, pressure in fluid dynamics, and these are the basic definitions of a scalar field. So now we are gonna understand what a gradient is. So now we're gonna understand what a gradient is. Now that we have um, understood what a scalar field is, so gradient of a scalar field, say v, say v is a scalar field. uh, so gradient of a scalar field is a vector that represents both magnitude and direction of maximum space rate of change, or space rate of increase of the scalar field. To calculate the gradient of a scalar, we are gonna use a vector operator called del operator. So del operator is, so if we apply this del operator on the scalar field v, we will get a vector which is known as grad or gradient of the scalar v. So grad v is del x v ax plus del, this is partial differentiation, ay, and these are the specific directions. In this case we are using Cartesian coordinates, del z v a z. So this is the gradient of a scalar field, which represents a vector. So if we want to know the gradient in cylindrical coordinate system, it will be del by del rho v in the direction arrow plus 1 by rho del phi v in the direction fi plus del z v in the direction az. This is the gradient of scalar v in cylindrical form, and in spherical form, in spherical coordinate system it will be like del by partial differentiation with respect to r, v in the direction r, partial differentiation with respect to theta 1 by r, partial differentiation with respect to theta of the scalar in the direction theta, plus 1 by r sine theta, partial differentiation with respect to phi of the scalar in the direction phi. So these three forms are the gradient of scalar field. We have designated it v in the three coordinate systems. Now we're gonna straight go to the calculation or solving the problem. We're gonna, so question A was we have to find the gradient of u. U is x square y plus xyz. So gradient gradient of u is del operator on u, del operator with the scalar multiple of del operator and the scalar field u, which will give us del by del x u plus in the direction x del by del y u the direction ay plus del z in the direction az. So if we look at this scalar field is in Cartesian coordinate system, so we have used the del operator in Cartesian. So this will give us partial differentiation with respect to x square y plus xyz in the direction x plus del by del y x square y plus xyz in the direction ay plus del by del z x square y plus xyz in the direction xz. This will give us, so partial differentiation with respect to x, so to xy plus yz in the direction x plus with respect to y, partial differentiation with respect to y, x square plus xz in the direction x ay plus, so this will be 0 plus xy in the direction az. So gradient is, so this is the gradient. So now we have to find the gradient of this scalar field which is in cylindrical system. um, so grad gradient of v is del operator which we have to express in cylindrical system. Gradient of v is del by del rho v in the direction arrow plus 1 by rho del phi v in the direction phi plus del by del z of v in the direction az. So I'm gonna just straight differentiate it. So partial differentiation of rho z sine phi is with respect to rho is z sine phi plus 0 plus 2 rho in the direction a rho and plus 1 by rho in, so uh, rho z, and partial differentiation of sine phi is cos phi plus z squared 2 cos phi minus sine phi plus 0 in the direction phi plus partial differentiation of z, so rho sine phi plus 2z cos square phi plus 0 in the direction az. This will give us z sine phi plus z sine phi plus 2 rho in the direction a rho plus z cos phi z square by rho, so this will be minus z square by rho sine 2 phi. So we know that 2 cos phi sine phi is sine 2 phi. This is in the direction phi plus rho sine phi plus 2z cos square phi in the direction az. This is the gradient of the scalar in cylindrical system. So z sine phi plus 2 rho in the direction arrow plus z cos phi minus z square by rho sine 2 phi in the direction phi plus rho sine phi plus 2z cos square phi in the direction az. So here del operator will have to be in spherical form, spherical coordinate system. So uh, del by del r of f in the direction ar plus del by del theta 1 by r. Let me write this little more clearly. 1 by r del by del theta f in the direction theta plus 1 by r sine theta del by del phi of f in the direction a phi. So I'm not gonna write this here, it will be very large. I'm gonna just straight differentiate it. So partial differentiation with respect to r is, so this will be cos theta sine phi by r plus 2r phi in the direction ar plus 1 by r partial differentiation with respect to theta, so minus sine theta sine phi ln r plus 0 in the direction a theta. So there is no theta in this part, so partial differentiation is 0 and plus 1 by r sine theta. So partial differentiation with respect to phi, so cos theta, and partial differentiation with respect to phi gives sine phi to cos phi. So differentiation of sine is cos plus cos, and cos theta sine phi by r plus 2 r phi in the direction ar plus, so plus minus sine theta sine phi ln r by r in the direction a theta plus uh, by sine theta. Sure. Yeah, fine. So this is the answer, and this is the gradient of a scalar field which is in spherical coordinate system. So the gradient is cos theta sine phi by r plus 2 r phi in the direction if ar plus minus sine theta sine phi ln r by r in the direction a theta plus cot theta cos phi ln r by r plus r by sin theta a phi. So this is it. It's very easy. So if you know how to do partial differentiation, you can easily apply the del operator in any scalar field in any coordinate system, so and find the gradient. And gradient is, it is a vector that indicates the maximum rate of increase or decrease in a certain direction. So in the direction ar, the maximum rate of change, or in this case you can say increase, is cos theta sin phi by r plus 2r phi. This is the maximum rate of change of this scalar in this in the direction ar. So and the maximum rate of change in the direction a theta for the scalar field is this sin theta sin phi ln r by r with minus, and maximum rate of change or rate of increase is cot theta cos phi ln r by r plus r sin r by sin theta in the direction a phi. Is nothing but um, a way of calculating the rate of maximum rate of increase in a certain direction. So using gradient we can find slope of surface, force exerted by electric and gravitational field. We can measure the maximum heat flow in a certain direction. So and EMF, this will be very useful for us to find the gradient of a scalar field. So that's it today. Thank you for watching this far.